Hello, in this video we are going to study about the addressing modes. Why do we use different addressing modes? Well, the computers use addressing modes for the purpose of accommodating one or both of the following provisions. To give the program versatility to the user by providing such functionalities such as pointers, counters, indexing of data, and the program relocation, and also to reduce the number of bits in the address field of the instruction. Let's see the meaning of all these points. So how do pointers help us? Suppose there is a instruction add x where this is indirect address itself. So this is an indirect address. Now how do we handle this? Now let's suppose that x value is 200. Now this is indirect address, so it means 200 is not having the actual operand. Suppose 200 is having 300 value, so we have to go to 300 value. At that location, whatever the value will be, this will be the actual operand. So effective address is equal to actual operand. This is the definition of effective address. In this case, my effective address will be 400. To handle this type of addressing, we need addressing modes. The counters. Now how does counters are handled by the addressing mode? Suppose there is a for loop, I equal to 0, I less than n, I plus plus. After all these statements inside, I want to do I plus plus every time. Now what happens is, this I plus plus is done by increment addressing mode. Now here addressing mode is used in form of increment addressing mode. Similarly, if this is I equal to n, I greater than 0, I minus minus, this will be using decrement addressing mode. So counters are handled using increment and decrement addressing mode. Now suppose I want to handle the indexing of array. Suppose there is an array A whose starting address has an index of 0. Now I want to move within the array, then I have to go to I equal to 1, I equal to 2, 3 and so on. So this can be easily handled by using the addressing mode. We will see later which addressing mode will be helpful for doing this indexing. Program relocation. How does addressing mode helps us in program relocation? So what does program relocation means? It means that if I have a program, if I have a subroutine at address 200 and I have a jump statement here to 250, I want to jump from here, so this will be 201, 202, 3, 4 and I want to jump somewhere here at 250. I will come here. Now due to some reason I have to copy this program to some other location and I have to move this at location 300. Everything will be copied, so that program having the jump to 50 will be as it is. So that will be wrong because this one will take us here and not here. So this problem of handling the jump and by program relocation, all the statements should run in the right way. There is a technique using the addressing mode which will help us doing this successfully. How do we reduce the number of bits in the addressing field? Now suppose there is a memory of 16 bits each word. This one word is equal to 16 bit, and this goes on from 0 1 to 1023. So there are 1k locations of 16 bit each. So these 1k locations can be addressed using only 10 bits. These addresses can be specified using only 10 bits. So lot of space is being saved. To reach some address, only 10 bits are required in this case in 1k locations. So the number of bits in the addressing field also reduces. So these are the 2 points which we have discussed in detail now. Addressing modes and operation cycles. In order to understand the various addressing modes, it is crucial to first understand the basic operation cycle of a computer. The control unit of a computer is designed to go through an instruction cycle that is divided into three major phases: fetch, decode, and execute. Instruction fetch. A register called program counter keeps track of the instruction in the program stored in the memory. Program counter holds the address of the instruction to be executed next. It is incremented each time an instruction is fetched from the memory. Now suppose I have a memory having some instructions here. Now suppose I have written add x, then add y. Suppose this has address 100, this has address 101. When this statement is fetched, even before decoding this, at this point program counter is incremented by 1. At this point, at initial phase, program counter was 100. At this point, before the decoding, PC has already become 101. So the program counter holds the address of the instruction to be executed next. So 101 is the instruction address of the next location. Decoding. So the decoding has three functions. It has to determine which operation has to be performed, what is the addressing mode of the instruction, and what is the location of the operands. All these three things has to be done by the decoding phase. So what happens in the instruction execute phase? The instruction is executed, and after the execution the new instruction cycle begins for the next instruction in the program. These two things are done in the execution phase. Now the different types of addressing modes. The concept of effective address. I told earlier also, effective address is where the actual operand is present. Let's see. Sometimes the value given in the address field of an instruction is the address of the operand, but sometimes it is just the address from which the actual address of the operand is calculated. Therefore, it is important to distinguish between the address specified by the instruction and effective address used by the control when executing the instruction. So the effective address is the address that is obtained from the computation dictated by the addressing mode. Now the different types of addressing modes, in which there are no address fields. There are two of them: implied address mode and immediate address mode. When the address field specifies an address, so direct mode and the indirect mode. When the address field specifies a register, register mode, register indirect mode, and the auto increment, auto decrement mode. Based on the identity of the CPU register used to compute effective address, relative mode, index mode, and the base register mode. Now we will see the details how these all differentiate from each other. Implied addressing mode. In this addressing mode, operands are specified implicitly in the definition. So CMA means that we want to complement the value of accumulator. So here we do not have to explicitly give the operand. It is understood that we have to complement the value of accumulator. Whatever the accumulator value will be, suppose accumulator value was 0, after CMA my accumulator value will become 1. All the register reference instructions that use the accumulator are implied mode instructions. Whenever the register reference instruction AC is used, implied mode instruction is there. All the zero address instructions in the stack organized computer are implied mode instructions, since the operands are always implied to be the top of the stack. So suppose I have written INCA, it means that we want to increment the value of accumulator. INCA will do this part. Now what is the advantage? Advantage is that we have no need to specify address. No address has to be given. This is an advantage. This saves our time and the size of the instruction is less, so it can compute faster. Immediate addressing mode. In this addressing mode, the operand is specified in the instruction itself. That is, immediate mode instruction have an operand field rather than the address field. So in this, whatever the operation has to be done is specified by the opcode, and the operand gives the value on which the operation has to be done. We do not have to go anywhere else. The value is within the instruction. So the example of immediate addressing mode can be such that add 25H. This means that we want to add 25 into the accumulator. This value is added directly. Now there can be multiple questions which can be generated from this. One of the question can be, suppose this is the instruction. One bit is for the mode, 3 bits are for the opcode, and 12 bits are for the operand. Now this is a 16-bit instruction. What is the maximum value of the operand given in the 2's complement form using the immediate mode? Now I want to know the maximum value which can be stored here in 2's complement form. Maximum value is being asked. What is the maximum value in 2's complement form? It is 2 raised to power n minus 1 minus 1, where n are the number of bits. So in this case, the maximum value will be 2 raised to power 11 minus 1, which is equal to 2048 minus 1, 2047. Register mode. In this mode, the operand is present in one of the CPU registers. A particular register is selected using the register field in the instruction. Now clearly, given this register set, we have operand at one of the register. Suppose this one was R2. Now this register has to be used. Suppose this one is R2, then we get the operand from that register. This means that if I want to do add R1, this means that I want to add this R1 value into the accumulator. This R1 was somewhere here in the registers. This value is directly sent to this using the register mode, and the accumulator value will get updated. Suppose accumulator value was 20, my accumulator will be 30 after addition. These are the two questions for register mode I want to discuss here. If there are n registers, how many bits are required to specify an operand here in the register mode? Read this question carefully and try to answer this. If there are n registers, how many bits are required to specify an operand here in the register mode? So based on number of registers, the number of bits of operand can be calculated by using this formula, log of n base 2 ceiling function. So this is the number of bits. Now given the size of the register is n bits, operand is specified in 2's complement system. What is the maximum magnitude of the operand possible? So the maximum magnitude will be same as 2 raised power n minus 1 minus 1. So this is the maximum magnitude of the operand. Now the register indirect mode. In this mode, the instruction specifies a register in the CPU, and the contents of this register gives the address of the operand. Now suppose this R was storing some value of register R1. Now it has the effective address which we have to go. So suppose this location was 200. At 200 we get the actual value of the operand. Now in the register indirect mode, let's see one more example. Suppose this one is the R1 register having the value 300. Now this is the effective address, so we have to go at that location and get the actual value of the operand. So at that 300 we have value of 400 in the memory. So how to write this? If there is instruction add R1 in the register indirect mode, we have to do is accumulator plus this. So we have to use this R1 value as the effective address, and we have to go to this locations to get the value of the operand. So this 400 will be added to the accumulator. So what is the advantage of the register indirect mode? So when the same address is needed repetitively in the code, it is wise to store that address in some register. Now suppose there is a program of 1000 lines, and after every 5 locations, after every 5 statements, we want to use some address. Suppose 5000 address is being called every time after every 5 lines. So instead of using the address 5000 again and again, We will use some register which will hold the value of 5000 by using the register indirect addressing mode, and we will use that register again and again. So the cost of going to that location again and again is reduced by saving that value into one register. So if the size of the register is 8 bits, how many addresses can it actually refer to in register indirect mode? So it will be 2 raised per 8, that is 256 words. Auto increment and auto decrement mode. This is similar to the register indirect mode, except that the register is incremented or decremented after or before its value is used to assess the operand present in the memory. So we can see an example here. Suppose this is an array and this location is 300, this is 301, 302 and so on, and I want to assess this array locations one by one. So my R1 is having value of 300 and I want to increment every time. So rather than jumping from addresses of 300 to 301 to 302, what we do is we keep the base address same and then add +1 every time using the auto increment mode. This can also be implemented using the flip-flops. If you have seen flip-flops, you will know that the counters are using the same property of the flip-flops to go ahead one by one. Even for going back into the addresses at 299, 298, this technique is good technique, incrementing or decrementing the values. When the address stored in the register refers to a table of data in memory, it is necessary to increment or decrement the register after access to the table. The array I showed you is also known as a table. So whichever direction we want to go, either in the positive direction or in the negative direction, the increment and decrement is being done using this mode, the direct addressing mode. In this addressing mode, the address of the operand is given directly in the address field of the instruction. So the operand field is having the address of the actual operand we need. So if there is A, this A has the effective value of the operand which we want to use in the program. Example, suppose I say add X. This means that accumulator is to be added with the value at location X. So this is the location X which is having 100, so this 100 will be added here directly. What is the disadvantage? The disadvantage is that address has to be in the range of that value, whatever the size of the operand we give. So suppose this is my instruction format. In this, suppose I say that my operand size is 10 bits. So my address has to be in the range of 102.1023 range to be accepted into the instruction. If I give some other address, suppose 2000, this is not acceptable here because the size is fixed. What is the advantage? So this was the disadvantage. What is the advantage here? Advantage is that the address is directly stored as operand. So address is directly stored as operand. This is usable in storing the variables. The storage of variables is done using the direct addressing mode. Now indirect addressing mode. Indirect addressing mode means that the operand field will have the address, and that address will be having the effective address. So it is kind of a double jump. We jump from instruction to the location, and that location is sending us again to some other location, and then we get the final value of the operand. Example, suppose I say add x, and x is 300 for indirect addressing mode. It means that in a memory locations, suppose at 300 my value was 400, so this is the effective address. So this 400 is somewhere here, which is having value of 500. So this is my actual operand. This is my operand to be used. So how do we express this? We express this 500 as m of x. M of x means this 400 because x was this, and again m of x because I want to reach 500. So this is 500. So I want to do add x. This is written as accumulator equal to accumulator plus m of x. Now there are some addressing modes that require address field of the instruction to be added to a specific register in the CPU. In such addressing modes, the effective address is computed as follows. Effective address is equal to address part of the instruction plus content of the CPU register. When the CPU register is program counter, it is known as relative addressing mode. When the CPU register is indexed register, it is known as indexed addressing mode. When the CPU register is the base register, it is known as the base register addressing mode. Now let's see what is relative addressing mode. In this addressing mode, the address given in the address field of the instruction is added to the content of the PC. So the value of the PC is added to the address given in the address field of the instruction, and the final address is this effective address a plus PC, and at that location the operand is there. Now for instance, let's say PC is equal to 823 and the address part of the instruction contains 33. Then the instruction at location 823 is read from the memory during the fetch phase and PC is incremented by 1. Obviously I told you that when some instruction is fetched, suppose instruction at PC equal to 823 is fetched, by the time it is fetched it is incremented to 824. So in the relative mode, the effective address will be the current value PC plus the address which was 33. So my effective address is 857. This address is 33 locations ahead of the address of the next instruction. Okay, so let's visualize one more example. Now suppose this is my memory 300, 301, 302, 320, 321. Now suppose I write here branch 321. I will reach somewhere here on branching, but this direct addressing increases the size of the instruction. I can't give the direct address. I do not want to increase the size of the instruction. I want to minimize it. So how can I minimize it? I will write here. So branch 321 is not acceptable. I want to minimize the size. I will write here branch 20. Why branch 20? At location of 300 I am writing branch 20. This means that when this instruction will be fetched, suppose this branch 20 is written here and it is fetched, at that moment PC will be 301 and I want to reach 321. So my effective address using the relative addressing mode will be PC plus my address I give, this 20 of PI20. This 20 is used here, so it will be 301 plus 20 equal to 321. I will reach the same location but by using less number of bits. Similarly, if an instruction is executing at address 300, if an instruction is executing at address 300 and we use br minus 10, this is the command we use, what will be the final address? When the instruction at location 300 is fetched, my PC will be 301, so the effective address on br minus 10 will be 301 minus 10 equal to 291. So the effective address will be 291. Using the branch, the size of the address is less compared to the directly giving the direct address. I hope my point is clear now. Indexed addressing mode. Now suppose there is an array and that array has something as 300, 301, 302, 303 and so on, and I want to access the whole array at the less cost. What will be the technique? The technique will be simple. I will keep the initial address as A, which is 300, and I will give the index register the value of the location I want to handle. So I want to handle value of 303, so the index has to be 3, because this is I equal to 0 index, this is I equal to 1 index, 303 is I equal to 3 index. So index register value will be 3, A will be 300, so in the register set this index register will be used and the final value will be calculated here as 303 and the value will be fetched from location 303. What is the advantage of the indexed addressing mode? The advantage is array implementation. We can do the array implementation easily. Let's visualize that example again. Suppose there is an array. That array has the address of 300, 301, 302 and so on. Also we have a index register that index register has some value, suppose it is 3. When I say add 300, where 300 is the starting address of the array, the effective address will be 300 plus 3, which is the value of IR, and this is the effective starting address of the array. So the effective address is 303. Base register addressing mode. In this, the value of the base register as well as the value given in the address are added to get the address of the operand. Now suppose we have a program at location 200. The program starts, and at 201 we have a statement BR250. This branching will take us somewhere here. Now we want to shift this program. Now we want to do the program relocation. And we bring this program somewhere here, where the program has the starting address as 300. Now because we copied that program, it will have this statement here. So this will take us not at 350, which we actually wanted to go, but somewhere here. So this is illegal. We do not want to go at 250, we want to go to 350. Now what is the solution? The solution is that keep the base according to the program location. This base register will hold the address of 200, and this base register on the other side will have the address of 300. And because we want to jump 50 locations, we will have the offset register. The offset register, this side will be 50, and this side it will again be 50. So instead of 250 we will write here branch 50, on the other side also BR50. So 50 is the offset, and base register value is holding the starting address of the program. So when I say BR50 here, it will take me at 350 by using 300 plus 50 value, and on this side it will be 200 plus 50, and it will take me at this location. The program relocation is the advantage. The basic difference between the indexed and the base register addressing mode is, in indexed mode the base is present inside the instruction and index is present inside the register. So inside the register index value is present, and in the base register mode the offset value is present inside the instruction and base is present inside the register. Applications of addressing mode. Immediate addressing mode, to initialize the registers to a constant value. Direct and register direct addressing mode, to access the static data to implement the variables. Indirect and register indirect addressing mode, to implement the pointers and to pass an array as a parameter. Relative addressing mode, for program relocation, to change the normal sequence of the execution, and for the branch type instructions. Indexed addressing mode, for the array implementation or the array addressing, and for the records implementation. The base register addressing mode. for writing the relocatable code and for handling the recursive procedures. Auto increment and auto decrement for implementing loops, for stepping through arrays in a loop, for implementing the push and pop, for implementing the counters. Let's see the numerical example here. Suppose these are the initial values. PC is 200, R1 is 400, index register is 100. Now this is the command here. Load to AC, mode is given, and the address is 500. The first word of the instruction specifies the opcode and the mode. The second word specifies the address. So this is the first word, this is the second word. For each addressing mode, we must calculate the effective address and the operand that must be loaded into the AC. For direct addressing mode, the effective address is 500 only, because in the direct addressing mode the address is given directly. So at 500, 800 is there, so the operand to be loaded is 800. In the immediate addressing mode, effective address is 201, because the 201 is the value which is being directly used as the effective address, and at this location we have 500, so that 500 will be loaded into the accumulator. In direct addressing mode, this 500 is the address of the operand. At this 500 we have 800, so this 800 is the effective address, and the operand to be loaded is 300, because at this effective address we have value of 300. Relative addressing mode. Relative addressing mode means that we have to add value of program counter into the address. So this 500 plus program counter, which is 202, which means 702 is the effective address, and at 702 we have 325, so the operand to be loaded is 325. In the indexed addressing mode, we have to add the index value with the address in the instruction. So 500 plus 100, so 600 is the effective address, so 600 has value of 900, so that value of 900 is loaded into the AC, and the effective address is 600. Register mode, there is no effective address because the operand is present in the register R1, so the operand to be loaded into the accumulator is 400 only. Register indirect mode. Now because this is the effective address, at this location we have value of 700, this 700 is loaded into the accumulator. Auto increment mode. So this is the continuation of the register indirect. Effective address is 400, and the operand to be loaded is 700. It is same as register indirect mode, but after the execution the R1 is updated to 401. Increment is done. Auto decrement, the effective address is 399, because R1 is decremented prior to the execution. Before the execution this 400 becomes 399, so the effective address is 399 now, and the value to be loaded into the AC is 450. So these are the values which we have discussed already. Now there is another numerical. A 2-word instruction is stored in memory at an address designated by the symbol W. The address field of the instruction is stored at w plus 1 designated by the symbol y. The operand used during the execution of the instruction is stored at an address symbolized by z. An index register contains value x. State how z is calculated for the other addresses from the other addresses if the addressing modes are A, B, C and D. Let's see the solution. So based on the question, this is the diagram which have to be made. W has the opcode mode. Opcode and mode is in the W. W plus 1 holds the Y. W plus 2 is the next instruction. So this forms single instruction W and W plus 1. So the program counter will be having value of W plus 2 because this will be fetched and it will be updated. Index register is X. Z is the operand. So what is the direct addressing mode based value of Z? So if the addressing mode is direct, the Z will be Y. So this Y will be used as it is because this is the direct addressing mode. In the direct addressing mode, the address is given inside the instruction itself. So this is treated as the direct address. For indirect addressing mode, the value will be m of y because this will be treated as the effective address. So we have to go there somewhere at my and get the value of the operand. So this z is m of y for indirect addressing mode. For relative addressing mode, what do? We add this value with value of PC. So the PC is w plus 2. So relative addressing mode means y plus w plus 2. In indexed addressing mode, what will be the solution? X will be added. So y plus x is the final z in indexed. Another numerical based on addressing mode. An instruction is stored at location 300 with its address field at location 301. The address field has a value of 400. A processor register R1 contains the number 200. Evaluate the effective address if the addressing mode of the instruction is direct, immediate, relative, register indirect, and indexed with R1 as the index register. So let's see the solution. In direct addressing mode, the direct address given is 400. Immediate value given is 301. Relative address will be program counter and the address given. So it will be 702. Register indirect means this 200 will be used as the effective address, and in case of indexed addressing mode, the value will be 400 plus 200 because we have to use this R1 value as the index register only. So it will be 600. So let's tally the answers. 400, immediate is 301, relative is 702, register indirect is 200, and indexed is 600. Match the following. Take your time and match the answers. So indirect addressing is done using the pointers. Immediate addressing is done for constants, and auto decrement addressing is done in loops. So it is x2, y3 and z1. So this is the answer. Name the type of the addressing mode. The operand is inside the instruction. Which addressing mode is this? So this is immediate addressing mode. The address of the operand is inside the instruction. So this is the direct addressing mode. Direct addressing is also known as absolute addressing. The register containing the address of the operand is specified in the instruction. This is known as register indirect mode. Location of the operand is implicit. This is implied mode. Let's see the answers. So operand is inside the instruction, immediate mode. Address of the operand is inside the instruction, direct or absolute mode. The register containing the address of the operand is specified in the instruction, register indirect mode. Location of the operand is implicit, implied mode. Now, which of the following addressing modes are suitable for program relocation at runtime? Absolute addressing. Absolute addressing means direct addressing, and direct addressing does not support program relocation. Base addressing does support program relocation, and relative addressing also supports program relocation. Indirect addressing mode does not support program relocation. So answer is 2 and 3. Match the following. Indirect addressing mode is used for passing the array as parameter. Indexed addressing mode is used for array implementation. Base register addressing mode is used for writing the relocatable code. Thank you for watching this.